Welcome back to class. I remain your amiable tutor on robotics. Today we shall be considering an important subject matter tagged mechatronics. Robotics being an aspect of mechatronics, mechatronics having its etymology from two words being mechanics and electronics. Mechanics, which is the science of motion, and also you having electronics, which is actually a field that deals with having to work with electric components to achieve some basic designated automations. Now, to this regard, mechatronics engineering technologists use a combination of mechanical, electrical, computer, and software skills to work with smart technologies such as robots, automated guided systems, and computer integrated manufacturing equipment. To this regard, we shall be examining what a microcontroller unit is. As you can actually see here with me, is actually a microcontroller unit on an Arduino board, which is currently blinking an LED. We'll be using a particular IDE, that is to say an integrated development environment tagged Arduino, which I'm going to be displaying right on your screen shortly. Now, this particular Arduino IDE enables you to be able to write embedded codes, which are then fed into your microcontroller by having to burn it. We use the word burn based on the fact that you're getting it into the microcontroller units. Now, first thing we need to do at this point in time is to define a pin mode during the setup section. And as you can see, you have it to be defined as an output pin. Then there's what you call loop. Loop is actually the method which it will definitely execute forever. That is to say, it will keep on executing that particular task until the microcontroller unit is actually being shut down. Microcontrollers are definitely just like a normal computer system, basically. As you can see, a microcontroller is an integrated circuit device used for controlling other portions of an electronic system, usually via microprocessor units, MPU. It has memory and some other peripherals. These devices are optimized for embedded applications that require both processing functionalities and agile, responsive interactions with digital, analog, and electromechanical components. This terrain promises to be very much practical oriented. As you can see with me, is actually a breadboard, which is very much essential with respect to prototyping. And as you can see here, is actually a resistor, which definitely limits the current that actually passes through a conductor. And this is an LED, that is a light emitting diode. And with me here is actually an Arduino board, which I'm definitely going to perform a particular practical with. So join me as I actually just try to show you what is being demonstrated here. Now, I have this particular breadboard here. I input this LED, these two different holes, that is to say my anode and the cathode. Now, having to know the anode with respect to these, the anodes are actually positively charged, then while you have the cathode to be the negative. Now, the positive is definitely longer than the negative. So what I just need to do on my Arduino board is just to locate the negative probe, which is actually this. I try to input it here. Then the next thing is actually to limit the current that is going to be fed into this my LED by having to get onto a particular rail of this particular terrain as well. Then the next thing is to supply it to the positive signal. And as you can see, this replicates what is currently being done on my Arduino board. Now, we might want to go further to actually just try to demonstrate having to increase the rate at which this LED actually brings. So what we just need to do, of which I'll be sharing my screen right away, is to kind of like go to our Arduino IDE to actually just try to vary the delay rate. Let me just try to vary the delay rate to be there about 200 milliseconds. 1,000 milliseconds makes 1 second. That is to say, 1,000 of a millisecond, just the way you have 10 raised by minus 3 to a milli. Then that means you need 1,000 of it to be 1 second. So this LED that is currently blinking, by the time I change this to what 200, you're going to definitely notice a significant change on the rate at which it's going to blink. So the next thing I might want to do is just to kind of like upload it. So definitely it's currently compiling Sketch, after which it must have compiled this Sketch. The next thing is actually to upload it. You're going to notice a difference in the rate at which it's going to be blinking at this point in time. So let's just try to kind of like get in here to see, you see that it is blinking faster, definitely. Now let's vary it further and see what actually happens as regards the variation. So let me just try to share my screen again, and I get on to what my Arduino ID, which is actually my Arduino integrated development environment. I change this to there about, let's say, 50 milliseconds. Definitely, it's definitely going to be what faster at this point in time now. 50. So let's see what happens. I just try to build, and then it actually gets uploaded to my microcontroller unit. You're definitely going to notice a significant difference at this point in time. Let me just try to show you what it actually gets to do at this point. You can see it's very, very fast, very, very fast, very, very fast. So definitely faster than how it used to be. But it's true why I reduced the rate of the blink, that is 3,000 milliseconds. You're going to definitely notice a significant difference in the rate at which it's going to blink. That is, there's going to be a significant change, that is a significant delay. That is, it blinks for 3 seconds. Then the next thing is maybe I actually just turn it off for like there about another 3 seconds. So let's just try to notice this particular significant difference in the rate at which it actually blinks. And this is actually being tagged as frequency, that is the number of blinks that actually occurs in 1 second. That is 1 over period is actually the formula for what? Frequency. So let us try to upload this at this point in time. Then what we're going to see now is going to be, let me say, very much different from what we've actually seen in time past. Let me just try to show you at this point in time the difference. So as you can see, it turns on. Definitely it's delaying the off. Okay, now it turns on for 3 seconds. 1, 2, 3. It goes off. 1, 2, 3. It turns on. It turns on again. 1, 2, 3. So you can actually notice the significant difference. So we're going to be doing quite a number of projects on this terrain, ranging from automatic street lights. Your street light actually gets turned on having to sense the presence of a human being is actually based on light dependent resistance. And this is actually an example of what light dependent resistor. That is to say, it's very much sensitive to light, of which that will be the next practical we're going to exhibit as far as this terrain is concerned, of which we're going to go on and on to also work with what you call switches. That is, when you press a button, which is just like what you actually find in your remote control and all that. So when you press a button, it's meant to execute a particular task. You have buzzers as well, which you're really going to just try to kind of like have to do quite a number of things with, of which we're going to move on to touch sensors. We're going to move on to having to work on RFID card systems, whereby you actually flash an ID card and either grant you access or deny you access. This is actually a potentiometer, that is a variable resistor. So kindly join me as we proceed more on this terrain. See you in the next class. Bye for now.